Hi, everybody. Thank you very much for coming to the talk on DevOps for data science. This will be a talk that will start general, and then we'll get quite technical as we go forward. So a little bit about your speaker. My name is Aaron Contorer. I used to be technology advisor to Bill Gates at Microsoft back when he ran Microsoft. And I built and ran a variety of fairly technical projects at Microsoft. Probably most notably, I was in charge of Microsoft's productivity tools team, which was sort of their first DevOps team for building software products like Windows and Office. And I ran that team in the late 1990s, back before DevOps had that name. I also ran the Visual C++ team, and I'm a sort of a former or recovering software developer myself. I have a number of patents and sort of a background as an inventor of things, and in my career have gone forward to be CTO of a few different startup companies, and for the past 5.5 years have been running a sort of boutique high-end engineering services firm called FP Complete. FP Complete provides engineering services and tools to other companies to sort of turbocharge their IT departments and their software development efforts. We work for 10 or more companies at a time, usually in high innovation industries, and most often working on the Linux stack with open source tools. We're based in San Diego, but we're completely geographically distributed, so we work for companies all over the place and have people on our team in a number of different countries. The important thing about FP Complete is that we have taken the idea of advanced software engineering and IT tools and built an engineering practice out of bringing those tools to more and more teams and to more and more companies. So we can recycle the knowledge of what works. So every additional company we work for hopefully gets more and more advanced service and more know-how about ways to accelerate and, as I like to say, turbocharge their efforts. And there's a lot to turbocharge, there's a lot that's needed. What we're trying to do in IT or in software engineering is a big challenge. Obviously, we need to be very productive. We need to build software, we need to get software releases out there, and users of our IT systems are very demanding and are always wondering why they don't have more. Where's my latest feature? Why can't you get that done immediately? But at the same time, we're trying to do our work with very high quality. Right? We're trying to not deliver bugs. We're trying to avoid creating security holes. We're trying to avoid creating system outages or service outages. And it gets even harder to find that sweet spot. That sweet spot here gets even smaller when we add that a lot of our systems also have to be very high performance. We're processing a lot of data or a lot of transactions or a lot of users. So it's a fairly demanding thing we're trying to do. And by contrast, the old model of IT, or if you will, of software development, is you just create features and then you're pretty much done. That's far from true. And what we need is a more modern model, which is really what DevOps is all about. And what we're trying to do, in effect, is to create an IT factory. We're trying to turn our organizations into factories that can build and put into production more and more new software capabilities. And when we talk about the word DevOps, most people here probably know, it means starting with development and then going on to operations. And in between is this very important step, deployment, which is the sort of magic that somehow makes software come off of developers' desktops or laptops and end up working on production systems. And that magic has become the failure point of a lot of IT departments. And when we look at, whether we look at Experian losing our personal data, whether we look at Airbus having an airplane fall out of the sky, whether we look at a major bank having all their ATMs go offline for a day, it turns out that it's DevOps and especially deployment where these things break down. So we're going to have to be better at it than we are today. I would like to propose that a factory, whether it's an IT factory or let's say a factory for woodworking and maybe making furniture, is made of its tools. A car factory without tools is a large empty building and a lot of people who wish they had a car. And the same is true in IT. An IT factory without tools is a lot of computers and a bunch of people who wish they had a service that was online and working. But if we look at our attitude toward tools in the IT industry, it's terribly out of date. We sort of give our craftspeople, the people building solutions, a handsaw, and we say, well, you're so smart, you'll take it from here, right? But imagine a furniture factory where we said, well, our furniture builders are so good at making furniture, we'll just give them a little $10 handsaw, and they'll be fine because they're good at it, right? And they could always work harder. But that would be crazy in any industry other than IT. People would laugh at you if you said that, right? At a minimum, if you're running a furniture factory, you're going to want to provide some kind of power tools, like the power saw in the middle of my spectrum here. At least it makes cuts quickly and reproducibly. You put a piece of wood, you pull the handle, it's cut now. You can get on with the hard part of your work instead of spending your high-value time doing a silly repetitive task and maybe even introducing errors or differences from unit to unit in that process. But a really good furniture factory wouldn't be caught dead using this tool. They use this tool. Right? This is a computer control, this is a CNC cutting machine. And you may see there's a little yellow box right in the middle on the top of that table. That's the saw, that's the cutting head. And all the rest of that gigantic tool is the automation and deployment system. All the rest of that tool is about taking that cutting head and moving it to where it needs to be and making sure the cuts are applied at the right place on a large sheet of wood. The amazing thing about this tool, it's automatic, it's completely reproducible, right? Every piece of furniture will be cut the same way. It's programmable. You can improve your piece of furniture anytime you want by putting new files onto this thing. And it automatically introduces a new process, because however this thing cuts a sheet of wood, that's how your factory cuts wood now. You don't have to go back and beg everyone in your company to do things a different way. A better tool will bring with it a better process, and a system full of better tools is a factory. Working for a Fortune 500 pharmaceutical company that was one of our engineering consulting clients at FP Complete, we built a factory to deliver world-class medical and analytics software. How did we build a factory like that? Well, it wasn't easy, but we were highly motivated. We wanted to, with our client, predict the effects of drugs on individual cancer patients. So this was the application we were trying to build. Now this was, again, one of the country's top pharmaceutical companies, so they're treating people who will die without their products. And they're providing these products to doctors and other healthcare professionals, and they want to help these people make better decisions. How do I keep my patient alive while I'm treating them for cancer? How do I get them better? So their goal was, we should be able to use very high performance computing and a lot of math and custom software to make better predictions about what's going to happen when we give these drugs to these patients. And we should be able, with the power of computers today, it should be possible to make an individual prediction for every patient. But look at the problems we had to solve. We had to do the software itself. We used Monte Carlo analysis, and we used a very powerful programming language called Haskell to do the engineering of the core application. That would be the saw itself that actually cuts the piece of wood. But there was so much more we had to do. We had to be able to model very complicated systems, and that means we had to have a software system that would somehow scale, not only to multi-core, but even to numerous servers in the cloud to be able to do gigantic computations. We had to allow the scientists to improve the model represented in the software, which meant we need to have a way to turn around build after build of the software with a great continuous integration system as the scientists coded up new enhancements to the numerical model that was describing what the drugs would do inside the patient's body. We had to make them productive and let them focus on writing software that represents the science, not on how do you get a build out. We had to have a system for improving the quality of the model so the predictions would be as good as possible, and this means we needed a complete data exploration and machine learning environment. And there had to be a productive way to bring all that data together and do all those runs. We had to work with the best experts in the world on the simulations we were trying to do and on the software itself, and that means we needed to run with a distributed team. We needed a tooling system that worked with a globally distributed set of experts on the project. It was about 30 people overall. We needed to meet extraordinary quality requirements because our client's goal was to build an actual medical device, a piece of software, in other words, that could be used by a real doctor to treat real patients and save their lives. That means passing the extremely high quality bar of the Food and Drug Administration, which is a much higher quality bar than we would use for, let's say, a consumer product where a little mistake now and then is annoying, but nobody dies. With a product like this, literally people die because they don't have this product, and literally people could die because of service outages or less than optimal predictions. So the quality bar was incredibly high. And we needed to scale this thing up for two different reasons. One, the data exploration as we constructed the models required immense amounts of computation. And two, in production, we needed to get answers while the patient was in the doctor's office. We needed a very complicated, high-performance computing, if you will, supercomputing level computations to be done while the patient was in the doctor's office with the answer coming back so that they would leave with the best possible instructions on what medicines to take and when. The beginning of the project wasn't very auspicious for meeting all these requirements because this was a state-of-the-art research and development project. And like all such projects, it started informally with a lot of exploratory work. So when we were brought in, there was this R&D team with no very clear tool chain. They were using primitive scripts to somehow try to build a set of tools onto their machines. And it was very hard to even get a build out. Just to say, I've written and edited the code and I'd like to build it again, it often failed, let alone the more complicated goals I've just described. There just wasn't any path to go from this low productivity to the massive scale that was going to be needed. By the time we were done, though, it was pretty successful. We did, in fact, build an automated factory, taking very, very heavy advantage of cloud features that we're going to look at in a minute to be able to build and run and deploy this software system with a very reproducible continuous integration system that allowed anybody to create builds at any time, whether for their own use in testing or whether to put into staging and production. The deployments became very, very sophisticated and rich, and we'll take a special look at those in today's talk. We were able to get the scalability we needed, taking advantage of the cloud to get not only enormous performance and throughput and scale, but also to get much more flexibility than we anticipated about where our code can run. So let's look inside this project and say, what did this factory look like? What were some of the key pieces we built with almost entirely open source DevOps tools? So we'll look at what we did for the developers, what we did for the build, what we did for the data scientists, how we staged and then deployed this system into production. We'll look at specifically a little trick we played where we created a common hosting platform, not just using a particular build of Linux, but a much richer DevOps-enabled server environment that we created that allowed the factory to be very productive as things were up-versioned. We'll look at the use of some very specific tools that I've named here, and we'll look very briefly at how we achieved the scalability as well as high availability from spreading our service across numerous machines. We began by focusing on the productivity of the engineers themselves. Many of the engineers were scientists, there were doctors, there were chemists, there were mathematicians and computer scientists, and straight software engineers. And all these people needed to be productive. The approach we took was to use Docker to create a container that contained all the necessary tools to do software engineering in our project. And this container was automatically built through its own continuous integration system. So the engineering system was itself an engineered system, recursively. So as we were able to go into our source control system and introduce new tools or new features into our development environment, new builds would automatically come out of continuous integration, and a new version of the Docker container would come out containing the latest tools. Because this was a self-contained engineering environment, it could be run anywhere. So those people in the distributed team who had perhaps less powerful computers in their desktop or this or that operating system, it didn't matter because they could always spin up a VM, a virtual machine, either on their own laptop or in the cloud. So a developer one day could run the engineering environment, let's say on their little MacBook Air like I have here that I'm presenting off of, and the next day say, I need a giant machine in the cloud because I'm going to be doing a lot of math or because I'm traveling. No problem. By having a continuous integration environment and a source control environment for our dev environment itself, we were also able to tell the Food and Drug Administration we have complete auditability of how our builds were done. Would you like to know what the tool chain was that built this executable? No problem. It's been automatically built. that's a reproducible build. We'll build you a new copy of that dev environment right now if you'd like to see it. Just name a version number and we'll press go. So this worked really well for us and got our engineers and scientists out of the business of trying to manage their own development environment and let them focus on getting their work done, while essentially one person at a time could focus on managing the development environment. Once that was working, we moved right on to creating the continuous integration system that would be shared across all those developers in their environment and in a centralized build server, the continuous integration server. So we knew that if a build worked on a developer's desktop or on a developer's VM, that same build was what was going to run for the shared build for the team's latest release. Again, the continuous integration system was built in a Docker container ready to be put onto any machine where we wanted the build to run. As soon as we did this, we had reproducibility. Anybody did a build, the software that came out was the same as if anybody else did the build. And we completely eliminated all the time wasted on engineering problems like, I had a different version of that library, the build worked for me, why doesn't it work for you? Now we could tell exactly what was there, and we could fix it for everyone by fixing it one time. When the software came out of the continuous integration system, the build server, if you will, we didn't stop by saying, here's a directory full of files. We actually, in the build scripts, went ahead and created Docker containers of the executables and the necessary instructions to spin up a virtual private cloud on which that system would run. So the output of continuous integration was not, here's some software, good luck getting this to work on the cloud. The output included the scripts necessary to bring up a new copy of the cloud itself. So the whole device, as we called it, included a whole virtual private cloud, all the network configurations, accounts, connections, and so on, as well as the executables themselves. The data scientists would typically do builds pretty often because they were exploring what would happen if I changed how the model worked, or they would try to run the model against different subsets of the thousands of past cancer patients' data that we had to explore what impact did changes in our math or in our parameters have on this data. So typically the data scientists would work on one very large host. We used the Amazon cloud. It could have been any cloud, but the Amazon cloud, of course, is very mature and worked well for us. So data science would typically be done at first on a single machine, but because the build created all the necessary scripts to bring up a cloud with distributed computation, which I'll get into again in a minute, how we distributed the computation, a data scientist could say, well, now I'd like to do a very large run. We're getting close to the deadline. We're going to do a release. I'd like to run my model against all the patient records we've ever seen. And we could literally spin up 1,000 Amazon C4, that's large compute machines, and have thousands of CPUs crunching on very large amounts of data all at the same time. That didn't end up costing anymore. The ability to bring up more servers, whether you run one server for 1,000 hours or 1,000 servers for 1 hour, you've incurred really the same costs. So we found that we were able to hit project deadlines much sooner by running new builds of our software against huge amounts of data on huge amounts of machines. Obviously, that would only work if it was automated and perfectly reproducible, because you can't have some machines in one configuration and some in another. Meanwhile, the quality assurance team would use the builds that came out of continuous integration to bring up its own copies of the device. And they would actually bring up a virtual private cloud that was an exact copy of the production system. Again, tuning the numbers of machines they wanted for computation purposes. And because the quality assurance, the test suite, was being run against the same build that the developers and data scientists were using and the same build that was going into production later, we didn't have to worry that if the system works in test, it wouldn't work in production. And this is all part of the deeper philosophy of DevOps, that we want automation and reproducibility because that's how we eliminate needless manual work that introduces errors, introduces security holes, and slows down the project. So quality assurance was able to work reliably. If it passed the test, it was going to run. Now we're going to drill down farther here into our deployment pipeline. And here's sort of the headlines. We containerized the system with Docker. Then we used Terraform, which is an infrastructure as software, infrastructure as code tool to build the underlying virtual private cloud. Then we used Packer to build machines that were virtual machine images that contained our software, SaltStack to configure them, Consul to control SaltStack, and AWS to provide a variety of scalability and fault tolerance services. Let's go ahead and jump into how that worked. First, we created a standard host configuration for a Linux machine that would run all the different tasks in our entire engineering team. Whether you were going to build a machine to do dev, whether you're going to build a machine to be a part of the services tier or the infrastructure or a system management machine, or whether you're going to build a slave machine that's just going to do math, it's just going to receive math requests and compute them. We would start with the same build of Linux. So we had a single Linux host on which all work was done. Every time we brought up a machine anywhere on the Amazon cloud, we would populate it with this basic machine image, the latest version of this. And then from there, we would customize that machine using SaltStack, which we'll return to in a second. As we brought up this virtual private cloud, this cluster or group of machines to run this device with many different roles collaborating to run these simulations and models and data management, Terraform was used to create all kinds of resources. I won't read through this, but you can see in the bottom half of the slide all the different resources that we would create every single time automatically. Anytime somebody said, I would like a copy of this device to run, this device isn't a single executable created by compiling 1,000 lines of code. This device was typically, a small deploy would be 12 cloud machines, and a large deploy could be hundreds of cloud machines. So Terraform would automatically configure effectively an entire new corporation worth of IT. So we would know that we're running on a clean, pure, up-to-date version of our system. I want to focus on the concept of immutability for a second. When we wanted to test a new cloud, we wouldn't take the old cloud and modify it. We would simply bring up a new one and destroy the old one. Some people in this room just heard in the previous talk about blue-green deployments. This is an extreme version of blue-green deployments where we would simply bring up any number of new copies of our science system. And then we would allow them all to be up to date, rather than wonder, what state is my system in now, because I can't remember, did I set the security groups correctly this time? That wouldn't be an issue. So Terraform automated the creation of all of this. And then Terraform would tell these generic virtual machines that it had just spun up who's supposed to do what. So it would tell one machine, you're supposed to be a system management node, and tell another one, you're supposed to be a compute node. These machine images were built automatically at the end of continuous integration, so Packer only needed to tell them what their roles were. And then once those machines started up, SaltStack would run on the machines to make further changes. So what SaltStack would do is go to a storage host on our newly created cloud, an S3 host on Amazon Web Services, and download a Debian package. And that package, a DEB file, would contain a range of different formulas, which are configuration files for SaltStack, telling it how to configure all the different kinds of machines that can exist in our device. The machine would then say, well, what's my role supposed to be? And it would run that SaltStack package. So the machines were now they're blossoming from they didn't exist to the infrastructure was made to I have a basic operating system image to now I'm running a config file to pull in whatever settings I need to. Now SaltStack in turn, obviously if it runs one time, the machine is configured as intended, but what if we wanted to create a long-running cloud? What if we brought one up and wanted it to be a production system rather than a test system? Well, now we had to look at the question of how to change the configuration of machines over time. And for that, we used a distributed systems fabric based on an open source tool called Consul. So every host was running a Consul agent. This is a very unusual thing we did, probably the most unusual thing we did. And these Consul agents, obviously, they'd be continuously doing system monitoring tasks, which is something Consul does. But more interestingly, we would use Consul's distributed data storage. It has a key value store built into it. And with a little utility that we wrote, that key value store was constantly updated with any changes that we made to our Git repository. So we could go into Git and change the configuration of a standard machine. We can say all dev nodes should now contain this new utility. or all compute nodes now need to have this new administrator account on them within this one virtual private cloud. And that change would be pushed by a little simple tool we wrote from our version management system into Consul. And the SaltStack nodes would be watching these console keys and say, oh, apparently somebody's changed my configuration. Let me go ahead and rerun my config file. And so in a very short time, from changing something in the source control system, in production machines could dynamically change to have the new tool on them, whether it be a monitoring agent, a user account, a tool, or anything we needed to change in their configuration. And if we accidentally damaged a configuration system, because I think we all know that modifying production systems while they're running can be hazardous, we could roll it back in version management in Git. And again, SaltStack would be notified and go back and run the old config. And the machines would gracefully return to their previous state. So using Consul to notify our machines how they should be configured and change their configuration was a pretty cutting edge thing that we did. The context for this project is worth thinking about. We were building a more advanced DevOps system for the research and development department of a Fortune 500 science company. So as we read articles about DevOps, it's tempting to think, well, everybody's ahead of me. Well, no, we had to be brought in to build this for a very advanced and respected company. So it's important to understand that if you feel like you're a little bit behind the curve in DevOps technology, and you see a presentation like this and you say, oh, why hasn't my company done this yet? Don't worry. This was very, very cutting edge, and we just completed this project recently. While we were at it, taking such advantage of the cloud, we decided to really take great advantage of Amazon's cloud features. So we wrote a system for distributing computation requests across Amazon nodes. It wasn't very hard to write. We used Redis and Elasticache as the infrastructure for creating a queue of computation request messages that would be read and executed by our application, which was this core, the little yellow saw on the cutting machine, right? The actual machines that did the math would watch a queue of compute requests. So we could create more and more compute machines as we needed to, have them subscribe to this queue, and then computation requests would just be done that much faster. We actually found that it was faster to create single core compute applications and then use the same mechanism to create scalability across multi-core machines. We often used 18 core machines on the Amazon cloud, as well as across numerous different machines, whether we had 3 or 600 Amazon nodes doing the computation. So that created really good scalability for us, and I would encourage anybody trying to create a really, really scalable infrastructure for separate tasks to consider a queue-based method for distributing the load. We also took advantage of AWS Availability Zones to create the highest possible availability for our production system. We never wanted a case to occur where a patient would be at their doctor's office and the doctor would say, I would love to tell you how to take your medicine, but the system is down. And we all know that as fault tolerant as Amazon is supposed to be, sometimes, unfortunately, whole data centers go down. So we would automatically, as we deployed large production systems, choose machines from different availability zones. And the fact that they were in different zones wouldn't matter if they were doing separate computations. But if one zone went down, then all the computations would go to the zone that was still up. That worked pretty well for us. So zooming back out from these details, I'd like to just take a moment and consider, was it worth it? You know, why did we build all this infrastructure if our goal was to help patients who have cancer, not to create an IT show-off project? Well, the truth is that the results worked. We were able to take this large distributed team of experts and make them far more productive, even as their science tasks turned out to be several times as much work as they initially estimated, because they were building a simulator and predictor, the likes of which had never been seen before. We were able to get the product done. We were able to get the scalability we wanted. We were able to get complete reproducibility, and actually to build a system which is ready for FDA approval, that is validated and verified to produce analyses that actually correctly indicate what's going to happen to cancer patients as they take these medicines. So at the end of the project, we looked back and we said, did we spend our resources correctly? Was it worth investing so much in DevOps when our real goal was to do science? And the answer was yes. We found that modern DevOps based on open source, freely available tools with the right know-how and with the right usage of those tools is incredibly productive. We found that the work gets more complicated than you think it's going to get, and if you haven't built a factory that's capable of taking the work you do every day and making it quick, easy, and reproducible, then you're going to get in real trouble when your work actually gets complicated. So productivity comes from automation, and automation is very feasible using the DevOps tools that are available off the shelf today. The cloud worked very well, and we honestly, I would say, had, other than the fact that you have to pay for it, really had no fundamental problems with using cloud computing for these very difficult computational tasks. We also found that when you build all your tools in containers and use virtual machines in the cloud, it's not a problem to have your team be distributed. In fact, it forces you to know that your knowledge is online, that there isn't some secret meeting room where the real trick to making the server work is written on a whiteboard. Right? And if that room is locked, or if the person in that room is on vacation, then you can't bring up your servers or can't figure out what's wrong. Using a distributed team forced us to use proper DevOps from the beginning, where everything important, even down to how to create an admin account, is under source control and automated. But I would say that we also learned that while all these tools are ready to use, they don't just work off the shelf. They do individual tasks off the shelf, but it would be completely unrealistic to say that you can just download any tool or any suite of tools and have the type of productive environment that we just described. It took us quite some months and quite some effort to figure out what tools would work for what and what their limitations were. So I would strongly encourage that if you are going to bring up an elaborate or state-of-the-art DevOps environment for your organization or for any group, that you really focus on getting as many best practices in from other people who've gone before you as you possibly can. I'll also mention, even though it's a little bit out of the scope of DevOps, that another lesson that was so big I had to mention it is we learned that functional programming using the Haskell language was tremendous. And that's not really a DevOps point, but I had to give a plug for this fabulous programming language. So to sum up, it works. If you invest in your IT factory, you are going to get tremendous productivity, and that productivity comes from predictable, reproducible, automated processes. By cutting the risk out of all the day-to-day infrastructure work that you have to do, you can limit your risk and your focus of brain power on developing the application you're really trying to develop. That's especially important if you're trying to build a new capability that your organization has never had before. So that's a slice of life from us at FP Complete. That's a project we did for a large high innovation company. If that sort of work interests you, whether you can help us on projects like that or whether we can help you on projects like that, I'd love to hear from you, and my email address is on the screen. Thanks for your time. Do we have time for any questions? I think we're going to do a couple of questions and answers with a microphone. So if anybody has a question, raise your hand so that the microphone can come to you, please.
Great presentation. On the Consul part,
yeah.
on the SaltStack formula, what was it that was changing out on the instances?
So typically, we try to avoid creating any mutations or changes in a production server instance. We would much rather create either a new server, or if we have to, a whole new virtual device. It's all automated, we can easily do that. So your question is exactly focused on the right question. Why would we ever in this world of automation want to modify the state of a device? Why don't we just make a new one? The answer is we would prefer to create a new device, but sometimes there are very small changes where it makes more sense to modify a production system. And a simple example would be you've created an additional administrator account. Perhaps you want to separate the security of two roles, and you have a large system in production, and it would be a lot of work to bring up a whole new system just to have two different admin accounts. Another example would be perhaps the system in production is the dev workbench, and you have a lot of developers who are doing work right now, and you say, all I want to do is make available to you one more tool. Your tools directory has 30 tools. I want you to have 31. Those would be examples of mutations that the Consul and SaltStack solution would work really well for.
Other question? I noticed that you're using Nomad, and I was just curious
With Nomad?
Yeah.
I'll be honest with you, it wasn't a major part of our solution. I think we thought we were going to use it for more than we did. And I think part of our ongoing learning process still is a lot of these tools sound like they're going to do 75% of your DevOps work by themselves. And then you find out that they're really only good for 1 or 2 tasks. So I'd say check back with us in 3 months and I'll tell you if we're still using Nomad. Up there? Oh. I think the mic is not going.
I noticed you have Haskell.
Haskell, yes.
I was wondering how Haskell in high level integrates into your existing system.
I was having some problem with the sound. Did you hear his question?
How does Haskell integrate to the rest of the system?
Thank you. So we are now enormous fans of Haskell. We love Haskell, and we use it as much as we can, frankly. For those not familiar, Haskell is a very high-level programming language from the functional programming family of languages that evolved from Lisp and Scheme. And it's an amazing language. It compiles to code that looks just like C code. So ultimately, Haskell lets you program at a very, very high level of mathematical power and abstraction, but what comes out of it looks exactly like parallel C. So executables come out that are indistinguishable to the operating system and the DevOps tools from something that you wrote in C or C++. So we simply integrate it by having the Haskell compiler be part of our continuous integration build scripts, and then deploying the executables that come out exactly the same we would have deployed executables that were written in C++. Frankly, Haskell is pretty good at cross-language programming, but the other thing that we learned is by using a service-oriented architecture, by componentizing our software into many separate pieces that are capable of running on different machines, the average member of the team doesn't need to know which pieces were written in which language. As it happens, we ended up doing the majority of the work in Haskell, but when somebody wanted to use another language, it was sort of a non-issue because they could talk to each other over an API. So the integration was surprisingly graceful, even though a very innovative language was being used by a large part of the team. Does that answer your question? Okay, I think there was one.
Okay, we're going to do one more question.
I guess that would be pretty good. Aaron, excellent presentation.
Thanks.
Thank you for sharing this journey. It sounds like what you're able to deliver is pretty comprehensive. My question for you is specifically, you addressed being able to reproduce everything in your tool chain.
Reproducibility, yeah.
Delivery. But how much retooling and I guess really how much consideration was taken into being able to deploy onto other infrastructure platforms, be it private cloud and non-AWS?
Right, so how much support or consideration was given for non-AWS clouds? The answer is that was absolutely a focus of ours. Actually, this large company that we did the project with wasn't sure that they wanted to stay on the Amazon cloud. As it happened, actually, they were a big user, and I think still are a big user of the Microsoft product lines as well. And so we designed in from the beginning a lot of abstraction that we wrote some modules in Haskell that would then call the cloud services. And so we were able, if we needed to pretty quickly move over to Azure as well. In fact, one of the differences we found between cloud services, although Amazon was a little bit ahead of some of the other brands and features, the others are catching up very quickly. And honestly, if we were to do this project again today, the thing that would probably come into our decision more would be the cost of the servers and the fact that some services bill by the hour and others bill by the minute. When services can be rented by the minute, you get really much more excited about dynamically using more servers. So we did try to be as cloud independent as we could, and we didn't find that lock-in was a really big issue. We could move if we needed to. Okay, I think we need to wrap up there. Thank you very much. I'll be here if there are more questions.